So first of all, we've got to register. Pass that round. If you could remember to sign, that would be great. Now before I carry on, can everybody hear me at the back? Because I can use the microphone if you need me to, but I haven't got a chance. Okay, if you can't hear me, just wave at me and I'll know to start shouting it. So, welcome to the first of 2 hours of lectures where we're going to have a look at the molecular basis for how some medicines used to treat cardiovascular conditions. We're going to look at how they actually function. And we're going to be looking at the fundamental chemistry behind some of these drugs. Guys, be quiet. Settle down, please. Now, you may have noticed Dr. Hannah sitting in the front row. As you know, from time to time, we're observed by colleagues to get feedback on our teaching. So she's just going to be observing today. That means when I ask you some questions later on, she's not going to answer. So you can't rely on her to answer the questions for you, okay, guys? Right, so as I said, we're going to be looking at the molecular basis behind how some drugs used to treat cardiovascular diseases work. And we're going to start off by having a recap of what you learned in part 1 about things like agonists, antagonists, pharmacophores, things like that. And then we're going to move on to have a look at some drugs that are used to treat cardiovascular disease. So we're going to start off the lecture by revising agonist and antagonist design. Now we went through this we would have gone through this last year in PM1B in your structure and function lectures. So if the material that you see today looks entirely new to you, I suggest you have a look at your PM1B notes from last year and that you refresh yourselves and come along with all of that knowledge next week. So we're going to have a look at revision of agonist and antagonist design, and then we're going to have a look at some molecules that can bind to beta adrenoreceptors. And specifically, we're going to be looking at, again, agonists and antagonists. We're going to look at the structure of the receptors themselves, and then we're going to have a look at the structure of molecules that are designed to be selective for one receptor over the other. And then we're going to finish off with looking at how chirality and the activity of the molecule can affect its mechanism of action. And this is the plan for the next 2 lectures. So we'll cover some of this week, and then we'll cover the rest of this in the lecture that's in 2 weeks' time. So let's go right back to the start of part 1. Hopefully some of you can remember that. We want to have a look at what happens when a drug binds to its intended target. And so here we have our macromolecular target, and this target contains a binding site, which you can see here. Now, if we want to introduce a drug to that binding site, we have to provide a molecule that is able to enter into this site and interact with our target. Now, when the drug molecule interacts with the target, it forces the target to change its shape. Now, this process is called induced fit. So when our drug molecule enters into the macromolecular target, the binding site changes its shape in an induced fit process. Now, the reason why this happens is because the drug molecule is designed to maximize its binding interactions with the target. So if we have a closer look at the binding site, we know that our drug will contain binding groups. So these will be chemical groups like hydrogen bonding groups, for example, that are able to bind to the target site. And the target site will contain binding regions that this drug molecule can exploit. Now, this drug molecule will then form a number of intermolecular bonds with the macromolecular target. And when it does this, it drives the target to change its shape. Now, I've mentioned that these are intermolecular bonds, but let's just quickly refresh some of the nomenclature involved in this area, some of the key terms that we all need to know. So hopefully you remember from part 1 that we can have both inter and intramolecular bonding. Now, intramolecular bonding means bonding within the same molecule. So a classic example of intramolecular bonding is a covalent interaction. So it's bonding within the same molecule. Another example could be the hydrogen bonds formed between neighbouring amino acids in alpha helices and beta sheaths, for example. These are another type of intramolecular interaction, so it's bonding within the same molecule. Now the other type of bonding is intermolecular bonding. Now this is bonding between two neighbouring molecules, and this must be a form of non-covalent interaction. So of course, if we take two molecules, come on in guys, come on in, get that down. If we take two molecules and form a covalent bond between them, they then essentially become one. So when we're looking at intermolecular bonding, we're looking at bonding between two different molecules in a non-covalent fashion. Now, either next week or the week after, I think it's next week, we'll be looking at some of the intra and the intermolecular bonding interactions in DNA, in PM2C2. So it's important that you know the difference between these two types of bonding. Now, both of these types of bonding can determine the three-dimensional structure of our target, so of our biomolecules. So as I've already mentioned, you can get hydrogen bonding between different amino acid side chains to form things like alpha helices and beta sheaths in proteins. But what we can also get is non-covalent interactions that hold different, what are called subunits of proteins together. So we could get a fully assembled protein that's made up of lots of smaller proteins. And these bind together to perform a function. And they would bind together through intermolecular bonding. But the key form of bonding that we're interested in for when we design drug molecules is intermolecular bonding. So we want to look at how our drug can bind to its target. Now there are several different types of intermolecular bonding that we're interested in. So we have things like electrostatic interactions or ionic interactions, where we have interactions between groups with opposing charges. We of course have hydrogen bonding, which is probably one of the most important types of bonding when we're looking at the design of new drug molecules. And we have things like van der Waals interactions, dipole-dipole, and ion-dipole, repulsive forces, and pi stacking, which is very important for DNA structure. Now, if these terms seem alien to you, please go back and have a look at your notes from PM1B. I promise they're in the structure and function section. Now, the reason why I'm mentioning these again is because these will almost certainly come up in your PAD portfolio viva in part 3. So if you get used to looking at these now and you completely learn what they mean, it will make your viva go a lot easier. Now, just as a quick refresher, I'd like to give you a very quick 2-minute test. So here we have a molecule of ramipril, and I'd like you to turn to the person next to you and just work out how many hydrogen bond acceptors, so good hydrogen bond acceptors, are in this molecule. I'll give you about 2 minutes just to have a quick look at that. me attention again, please, everybody. You've had a couple of minutes to look at this problem, and hopefully you've come up with an answer. So, can anyone tell me what we need for something to be a hydrogen bond acceptor? Anybody care to shout anything out? Yeah, back. Yeah, the nitrogen and oxygens are mostly hydrogen bond acceptors, but what specific feature do we need? Starts with L.
Lone pair.
Lone pair, exactly, perfect, spot on. So, out of all of these types of atoms, which types are going to contain lone pairs? Oxygen, yeah, and there's one more. Somebody already mentioned it, I think. Nitrogen, yeah, exactly. So we have these oxygens and nitrogen atoms on here. But I said, which ones are going to be good hydrogen bond acceptors? Now, who had 1, 2, 3, 4, 5, 6, 7? Who had an answer of 7 for this question? Perfect. So nobody had an answer of 7. Fantastic. That is good. Oh, good. Phew. Otherwise, you might have to go back to part 1 again. Okay, yeah. So you've all looked at this. You've gone 7 nitrogens and oxygens, but you've spotted that not all of these act as good hydrogen bond acceptors. So the correct answer is 6, because this nitrogen here, the lone pair from this nitrogen will be delocalized into this bond here. So this is essentially a peptide bond. So this lone pair will be delocalized into this carbon-nitrogen bond here, pushing the electrons from this carbon-oxygen bond up into the oxygen and giving it a negative charge. This makes the lone pair of electrons on this nitrogen unavailable for bonding. Now, I'm going to put this version of the presentation up on Blackboard after the lecture, so you don't need to worry about jotting this down. You'll get exactly this version up probably later on this afternoon. So it's all about availability of the lone pair. And so when we're building new molecules to be designed as either agonists or antagonists, we need to make sure that we have the correct groups that are able to exploit those binding interactions, the right groups to make those intermolecular interactions. And hydrogen bonds are one of the most important types of interactions for drug-target interactions, particularly at receptors. And so let's quickly review the binding of a substrate to a protein. I've already mentioned to you about the process of induced fit, but it's important to remember why induced fit is important. Now, I'm hoping that you all remember the 2 different hypotheses for how a molecule can bind to a protein. So we have the lock and key versus the induced fit. Now, the lock and key hypothesis states that both the enzyme and the substrate are structurally rigid. They can't change shape, and that they simply bind together like a key going into a lock. So it states they have a rigid structure, and more importantly, the substrate is a perfect fit to an active site or binding site on a receptor. Now, this doesn't explain why an enzyme or a receptor may respond to different substrates. You know, if we make a substrate that's slightly different, a receptor, it may still induce an action in a receptor. And so the alternative explanation is the theory of induced fit, which says that when our substrate binds to an enzyme or when our molecule binds to a receptor, it doesn't need to be an ideal shape for the binding site. And it says that the enzyme or the biomolecule can change its shape to accommodate that incoming molecule. So it says that it's forced to change shape. Now, the reason why we're reviewing this is because it's important to keep in mind that the target can change shape, particularly for the lecture in a couple of weeks, where we're going to have a look at some very closely related drug molecules designed to target either the B1 or the B2 receptor. And we're going to go through some of the different factors that, even though we're only changing a couple of atoms, change which receptor type the drug can bind to. But this process of induced fit is key for the design of new molecules. And it's key when we're trying to understand where to place atoms and binding groups within those molecules. Now, the induced fit process, or the change in shape, is driven by maximizing all of the intermolecular binding interactions. So, for example, we have a small molecule here that is inside a protein binding site. Now this molecule has a negative charge on this oxygen, so it's able to form an ionic interaction with this positively charged amino group. We also have a carbonyl up here, so we have this oxygen which can form a hydrogen bond with this hydrogen here. And we have a methyl group that is able to have a van der Waals interaction with the protein. Now when the molecule enters into the binding site, it's able to pull these groups closer to it and maximise the interaction, which you can see here. This is what changes the shape of the protein and can either cause an enzyme to activate and start a chemical reaction, or more crucially, cause a receptor to activate and trigger downstream signal. Now this process explains how a range of substrates can be tolerated by an enzyme or receptor. And it's important to keep in mind that the substrate is not a passive spectator. The substrate plays a key role in this process, in maximising the change of shape of this biomolecule. So the substrate isn't an innocent party in all of this. It plays a key role in maximising that induced fit process. And of course, we've got to remember that the binding interaction needs to be strong enough to hold our substrate or our agonist, but it must then allow for the release of either products from an enzymatic reaction or of neurotransmitters, because we don't want to permanently activate a receptor or permanently inhibit an enzyme. Now I just wanted to show you what this actually looks like in practice, because you've been told a lot about induced fit, but you've probably never had a chance to see it. So on the next slide I've got an animation of ramiprillat bound into protein, and you can see the change in shape that occurs, and you can see it's a very small change, it's not a large change. And so here we have the bound form with the ramiprillat and the protein, and then we have the unbound form. Now in green, these are all the alpha helices that are present in the angiotensin converting enzyme. Now ramiprillat is an ACE inhibitor. It blocks the binding of angiotensin 1, which prevents the production of angiotensin 2. Now angiotensin 2, as you should all know by now, is a potent vasoconstrictor and increases blood pressure. So by using ramiprillat, we can stop the production of this and reduce blood pressure. Now this is an antagonist which binds into the enzyme. And you can see the change in shape that this enzyme goes through. We're talking about a very small change. But it's this magnitude of change in a receptor or in an enzyme that is key to it functioning. And so this can help explain why changing one or two atoms in a drug molecule can convert it from an agonist to an antagonist, for example. We are talking about really very small changes that then get magnified up to have an effect in a biological system. Now this is just a zoom in on the binding site of the enzyme, but if we zoom out we can see how small this change really is. So if we zoom out, now I haven't shown the drug molecule in here, but this is a little animation going from the unbound form of the protein to the bound form. And if you're not convinced that this is moving, have a look at this bit on the top right, because it's the easiest bit to see. Now as you can hopefully see from the centre, the protein expands very slightly when the molecule binds. So we go from unbound to bound, unbound, bound, etc. It expands so slightly, it's such a small movement, but it is key to the activation of this enzyme. When the angiotensin 1 binds, it will induce a similar induced fit in this enzyme that converts into this small movement. But that small movement allows the reaction to take place. Now, over the next couple of hours, we're going to focus on some of the drugs that are in the Part 2 monographs. So what we're going to have a look at is amlodipine, and we're going to have a look at this as an example of how the 3D structure of a drug helps it to orient itself correctly within a binding site. We're going to have a look at ramipril as an example of a prodrug, and we're going to have a look at dobutamine as an example of a chiral drug molecule. And we're also going to have a look at atenolol and salbutamol, which act as an antagonist and an agonist, respectively. So first of all, we're going to have a look at amlodipine. Now, if we're designing a drug, what are the main sorts of things we need to think about? We need to think about things like functional groups, pharmacophores, bioisosteres, things like that. So if those words aren't meaning anything to you at this point, have a look back at your Part 1 and Part 2 lecture notes. Now, this is a chemical drawing of amlodipine, which is an antagonist that can bind to L-type calcium channels. Now, when you look at this picture, what I want you to start doing is trying to pick out some of the functional groups that are present. So, for example, we have esters up here. We've got an aromatic ring. We've got amino groups here and here. And we've also got this ring here. And what I want you to start doing when you look at chemical diagrams is start just trying to think in your head, what could the important structural features of these molecules be? Now, this drawing looks a bit odd. You know, it's all good up until about here, but then this bond here looks really long. Now, there's a reason for this, which is that this ring is not actually flat in the same plane as this ring. So this ring is perpendicular. So the dihydropyridine ring here sits flat, and this ring sits at 90 degrees to it, in this shape like this. And it's the chlorine group coming off this benzene ring that locks that into place. And so one of the structural requirements for this molecule to bind and orientate correctly is this chlorine group, which locks this ring so it is perpendicular to this one and locks it in position like this. And it'll become a lot clearer when I show you in a moment a three-dimensional animation of this molecule and show you what it looks like in 3D. Now, another thing that's worth noting when you look at this molecule is that this amino group here is important for both the formulation and as an ionic interaction in membrane. So this molecule enters into a negatively charged binding site. Now, at physiological pH, this amino group is protonated, giving it a positive charge. And that also helps to guide the molecule into the binding site. Now, the protonation at physiological pH also means that this whole compound can be formulated as a malleate salt. So it can be formulated in a soluble form as well. Now, if we take this diagram and convert it into 3D, we can see what this molecule actually looks like. So that's what I have here. Now, this is what the molecule actually looks like. You can see that this bond here corresponds to this carbon-carbon bond here, and this large yellow sphere is the chlorine atom. Now, all atoms have an inherent radius with them. We're used to seeing them drawn as points like this, but actually they're a lot larger than this. They have a radius in which nothing else can get inside, and that's what I've shown you here for the chlorine. So you can see here that this chlorine sits between these two arms at the, the rear of the molecule. Now it means that this benzene ring here is locked into place, locking it at 90 degrees to the plane of this ring here. So we have this one, which is oriented like this, and then this one, which is oriented 90 degrees to it. And this shape is one of the key attributes that allows it to insert itself into the binding site and orient the molecule correctly to give it its antagonistic behavior. Yeah? So if you look, that is going on to that. So you've got this ring here is now flat, this one is pointing out. Does that make sense? Yeah. So yeah, sometimes you have to kind of think of these things as sort of planes. So locking this ring into position is one of the key attributes that allows this to enter into the binding site and orient itself correctly. Now, if you take away the chlorine from this ring, it significantly reduces the activity of this drug molecule, showing that to be one of the key factors that allows it to act. on the calcium channels. Now, I've mentioned that this is an antagonist, so we should briefly review the difference between agonists and antagonists so that we can then understand the differences in their design and the reasons behind them. So first of all, we're going to quickly recap agonists. So agonists mimic the natural substrate, and when we're talking about receptors, they bind to receptors in such a way as to activate it. Now, when we're designing a new agonist, we need to consider three main points. Now, the first is that the drug or the molecule must have the correct binding groups. It needs to have the correct groups to be able to bind to the receptor. Now, it's no good the drug just having the right groups. We've also got to put those groups in the right place. So it needs to have the right groups in the right position. And of course, the drug has to be the correct size to fit into the binding site. If we need a drug that's this big, and we have a binding site that's this big, and we make one that's this big, it's not going to fit, right? So we need to have the right groups in the right position, and the molecule needs to be able to fit into our binding site. So I'm going to give you a couple of minutes just to have a look at this question. I want you to think about, with a partner, how does the design of an agonist result in its agonistic behavior? How does the design of an agonist result in it being able to function as an agonist? Just discuss between you for a couple of minutes and then I'll give you the answers. Okay, am I going to have your attention again, guys? Now, hopefully you've all come up with some form of answer to this question. I'm not going to ask you to read your answers out, but just quick, either nod or shake your head. Who came up, nod your head if you came up with an answer that uses more information than was on the previous slide. No? Okay, so we'll go through the answer to this question. You've already had the information you need to answer this question in this lecture, but what we're doing now is trying to link different concepts together. So, how does the design of an agonist result in agonistic behaviour? Well, the first bit is the contents of the previous slide. We need to have the correct size of molecule with the correct binding interactions in the correct orientation, and this will result in similar binding to the natural substrate. Now, the second part of the answer to this question is if the binding is similar, it will result in the correct induced fit, and therefore the receptor will be activated in the same way as with the natural substrate. So we're linking together the concepts of agonist design and induced fit in this question. And as I said, the answers I will put up on Blackboard after the session. So what I really want to kind of get across to you is that when you are looking at molecules, you're told this works as an agonist. I want you to look at that molecule and start to think, well, why does it work like that? What does it actually do? Why has it been designed in that way? Maybe have a look and see what the natural substrate is, or the natural agonist, and compare it to your drug molecule. And you'll see that often there are a lot of features that are the same. Now with drugs, obviously a lot of time you're trying to mimic the natural state of something to be able to correct a condition or to be able to fix somebody's health problem. And looking at the design of the molecule will also help inform you as to why you can have multiple drugs for some conditions and why some drugs will bind to receptors or to biomolecules that aren't their intended target. Now, of course, we've looked at agonists, so we should just quickly refresh ourselves on the reasons behind antagonist design. Now, antagonists must bind more strongly than the natural substrates, but if we're talking about receptors, we want it to bind but then not activate that receptor. And there's a couple of different ways that we can do this. So we could design a molecule to use the natural binding interactions, so to use the same methods of binding as the natural agonist or the natural substrate, but that blocks the required induced fit in that binding site. So for example, we could make a molecule that contains the same binding interactions but is slightly longer, slightly bigger. So it stops that induced fit process. And with that, we're almost going back to a kind of lock and key theory. If we can make a molecule that fits perfectly into the active site and binds into it, it won't give an induced fit. And with a receptor, it won't activate that receptor. Now we could also design a molecule to use different binding sites within the active site. So perhaps we could exploit the presence of different amino acid side chains in that binding site and make a molecule that binds differently and gives a different induced fit. So it gives an induced fit that changes the shape in the receptor in such a way that it doesn't activate it. So we can use either one of those two approaches. We can, of course, make molecules that also bind elsewhere to the receptor and change its shape as well, again, by changing it to a different type of induced fit, preventing its activation. And so I have more of a pharmacy practice pharmacology style question for you now. Why would you give a patient salbutamol to relieve the symptom of bronchospasm due to overdose of atenolol? Now again, I'm going to give you guys a couple of minutes, work in pairs and discuss this between you and try and come up with an answer. And in a couple of minutes I will go through the answer with you. Okay, everybody, you've had a couple of minutes to discuss it with a partner, so let's have a look at what the answer would be. So, for this question, was anybody able to come up with an answer? Just nod or shake your head, I'm not going to make you read it out. Yeah? Some of you? Yeah? Okay, so a few of you were able to come up with an answer. I'm going to give you the quick answer to this question first. So the quick answer is this. Atenolol is an antagonist for beta-androgenic receptors, whilst salbutamol is a B2 receptor agonist. Bronchospasm due to atenolol is from excessive action on both the B1 and B2 receptors, and adding an agonist will return this to normal levels of activity. Now this is the answer to a pharmacy practice question and covers some of the pharmacology as well. But what it doesn't tell us is why is salbutamol an agonist? Why is atenolol an antagonist? What's the molecular basis for recommending this type of treatment? And so now we're going to have a look at the slightly longer answer to this question. So the long answer for this question, we need to have a look at the natural substrate first. So this is adrenaline, which is our natural substrate or neurotransmitter. Now if we take a look at salbutamol and atenolol, we can see that there are some similarities and some differences with the adrenaline. Now atenolol is an antagonist, salbutamol is an agonist, so it has a similar effect as the adrenaline. So what I'd like you to do now, again with a partner, is just have a look at the salbutamol and the adrenaline and the atenolol and see if you can highlight some differences between these molecules and some similarities. And in a moment we'll go through and explain why salbutamol acts as an agonist and atenolol an antagonist. So again, I'll just give you a couple of minutes. Have a go. It doesn't matter if it's wrong. Just have an educated guess at this question. Try and explain why salbutamol could act as an agonist and atenolol an antagonist. Okay guys, let's have a look at the answers to this. Guys, if I can have your attention for 5 more minutes. So, let's go through and have a look at the answers. So I'm just going to put all 3 of these in a line. Would anyone like to say one of the differences or similarities that they highlighted? Anyone want to shout something out?
The salbutamol and adrenaline both have catechol groups.
Both have what, sorry?
Catechol.
Yeah, so they've both got similar chemical groups between these 2, yeah? Does that make sense?
Yeah, they have the hydroxyl groups. They have the same, basically.
Yeah, so yeah, perfect. So the hydroxyl groups are in a very similar position on the molecule. You can see the 2 hydroxyl groups here on the adrenaline and the hydroxyl groups here. There is an extra carbon in here, but on the whole they're in a very similar sort of place. So yeah, very good. Anyone else want to offer an answer? Okay, in which case we will go through. So, adrenaline and salbutamol. The first thing that's consistent, the first thing that you need, or that you should notice before you even look at the functional groups, is their size. These 2 molecules are the same sort of size. They have a similar number of carbons and of atoms in them, but the atenolol is longer, it's larger. Now, agonists are designed to maximize the induced fit in a binding site. And so they are usually smaller than an antagonist, which has to bind but not have that induced fit. So the first thing that should immediately spring to mind is looking at the relative size. And not just because I've drawn this one slightly larger than I've drawn these. These 2 have a similar number of atoms and they have their functional groups in similar positions. So, as you said correctly, the hydroxyl groups are in a similar position between the adrenaline and the salbutamol. And if we look at the right-hand side of the molecule, this hydroxyl group here and the amine, again, are in similar positions. Now, if we look at the atenolol, we can see that we've added an extra carbon and an extra oxygen into this chain, making this molecule longer, making it larger. Now, if we look at the hydroxyl groups, we've also replaced the hydroxyl groups with this group here in the atenolol. And this may give a different binding interaction in the binding site. So we've got the size of molecules, so the agonists are smaller than the antagonist. And we have, in the agonist, similar placement of the hydrogen bonding groups. And when we look at the antagonist, we've moved this hydrogen bonding groups away from the other end of the molecule. And this is to reduce the induced fit that atenolol has on the receptor, allowing it to act as an antagonist. Now, one other thing, which is a very minor point, is that on the salbutamol, we have this tertiary butyl group here. And this may help the salbutamol to bind and exploit additional van der Waals interactions in the binding site. So helping it to bind and helping to orient it, because this group is reasonably bulky. But what you've been able to do is have a look at our natural substrate and compare it to an agonist and an antagonist, and you can now rationalise the agonistic and antagonistic behaviour of these molecules and their mechanism of action on the receptor site. And so that is the long answer to this question, and fully explains not only why you have the agonist and antagonist and use them for treatment, but also the molecular basis behind how they function. And so that's it for this lecture. In a couple of weeks' time, we'll come back together for another hour, where we'll be having a look at some more examples of drugs that are used to treat cardiovascular disease and rationalise how they work. Now, the last slide on here is a testing slide. Can you do all of this? This covers the next lecture as well, so you aren't expecting to get all of this from this lecture. So thank you very much, and I will see you in a couple of weeks' time for the second half of this lecture.